Okay. So what do you guys want to start on? Homework?
Yeah.
Is it view survival log? View today? Okay. This is just like the one we did in class, right? First one?
Oh, the homework?
Yeah. It's like, it's fairly the same. Numbers are changed, but
No, we're for number 6.
number 6. For this one? The 3 straight wires?
Yeah.
Okay. So you have the 3 wires, right? Let's just draw this out. So this, here, the ports. Oh, this one's coming out. This one's coming out. This one is out. Okay. That, and these, all these are equal arrows, so this is distance D, this is distance D, this is distance D. And now they're asking, another wire is added. This one is aligned with the z-axis, which is true. So you have a wire added right here. Right? And it's aligned with the z-axis. So it follows the same direction as these, meaning it's coming out. Okay? And you know its position. For me, it's negative 27.7 centimeters. It will be different numbers for you, but you can just change your numbers later, right? So you know this distance, let's call this U2. Two. Okay, so now it's asking which of the following is true. If it's directed along the positive z-axis, then it's possible to make the y component of the net field equal to 0 at the origin. Okay, so if it's directed along the positive, that means it's the current's coming out of the page, is what I'm going to take it as, right? So if the current's coming out of the page carries 4 amps. Okay. So if the current's coming out of the page, you cross it. So at this point, the field will be this way, right? Right. But then you have to realize that it doesn't tell you how many amps it carries. Okay, it just says it carries a certain amount of amps, I4. Right, so that can be whatever. Okay, so you know that it's gonna be this way. And given this one, the left one, I1, this is 1, 2, and 3. Okay, given I3, it goes in, so at this point it's gonna be straight down,
Yeah.
right? Okay, same thing for this one. If you curl it, it'll be straight down, right? And for this one, if you curl it, it'll be straight across. I hate this thing. So the x components will cancel out, right? But the y components will add up to negative, right? So that's not possible. So A is not the answer, or 1, or whatever the top one is, right? That can't be the choice, because it's saying then the y components will be equal to 0. But in this case, the y component is 2 times down. Okay, so we get rid of that. So now we know that which directions these are going in, so read the second statement. What's the second statement say?
Negative z-axis.
Okay, let's do the positive, because we drew this according to positive, right? We drew I, we drew the field. So the second positive is,
Let's see.
yeah. So really you would want to check it and like do, make it negative, like this current into the board, right? So this current was into the board, then you would have it like this, okay? And then you know that you have twice negative, then you would, if this was z, if this was negative, this is positive and negative. If it was positive, you would end up with 2 going down. Right? And if it was negative, you would have 2 to the right and 2 going down. Right? Once you just find one, you can just flip the sign and you can do all of this. So this is the only one where the x components will cancel out if it's positive, and here nothing cancels out. So the answer is C. Right, you just have to draw out your field. And I know sometimes it's tricky like to go like this, because over here, if it's at a point like this, it seems at an angle. What I would do is, a trick that I use is like, suppose you have a pin, right, and you pin it right here. And you remember the old trick before, like you used to put a tack and then you tie a pencil to a string and you go, remember? Before they had like real nice, whatever they call those things. That's what I would do, right? So just place one here and go around. And if you go around, you see, okay, it goes directly in that direction. And then you take the tangent. So because the circle is like this, the tangent vector goes straight, so you know it goes straight. So if the point was something like here, right? And this was, let's say, positive current. Let's say this was negative current. Negative in this sense meaning going into the board. Which way would the direction be? Let's come up and draw. We're going to make the class more interactive. Draw the direction of the.
Oh, you're asking the dot?
Yeah, this,
Oh.
yeah, and okay, so go in, come across, and do a trick right this way, and that's a tangent, and so like that. And if this was positive, then it would be the opposite direction. We're doing, all right, can you give me the paper? Oh, you're right, okay. We're doing homework, the straight lines, 3 infinite straight wires. It's sort of what we did in class for whiteboarding. Okay. Another question. Oh, do you want me to keep this up, or did you want to?
Yeah, it's the second question I called. The rectangular.
The triangle one?
No, rectangular.
Rectangular loop?
Yeah.
Okay, so let me erase this. All right. So we have the rectangular loop shown at this distance. current flows that way, and I. Number 2.
Yeah.
What is the x component of force exerted by an infinite wire on segment BC? Okay. So let's draw this out. The current I was I1. And here you have current I2 this way. I2. I2. This is A, B, C, D. Given this distance of L, this height of H, and this distance of W. Right, on this side. So they're asking, and so also they give you the coordinate system. So it's like this. X, Y, and Z come straight out of the board. And so right cross right-hand rule for the coordinate system, X cross into Y, Z comes out of the board. Yeah. So what equation do you have for forces on this?
I1, I2, L over 2 times constant times over 2 pi.
Right, so this force is forces between two parallel wires, right? And so if you look at it, this wire is parallel, and they're asking for force on BC, which is also parallel to that wire. So the equation for the force is mu naught over 2 pi d L1 down. Force is equal to mu naught over 2 pi d, I1, sorry, all that was I1, I2. So here, what's confusing in this one? What do you,
I'm not sure what the direction is.
okay. So we're able to solve for question 1.
Yeah.
Right, so for question 1, the current is going down, so it's going opposite, right? So it would be a push force, like a repel force, right? Because remember in class you said if 2 wires have current in the same direction, then the force should be attractive. Remember that? This is force. And if they go in the opposite direction, it's repel force. So in this case, it would be a repel force, but in this case, it would be an attractive force, right? Because here, the current's like this, which is going in the same direction. Okay? So then you just have to use this equation to solve for your force, right? So in this case, your D is it's the distance between the total distance from your wire to your second wire. So it will not just be this L, because this L is only the distance of this half. It would be L plus W, right? And you know mu naught, 2 pi are constants, so you don't have to worry about trying to figure out what those are. So you end up with mu naught over 2 pi L plus W. Okay, now you have to worry about this stuff. So L is, well, they're asked for the length of the wire, correct? And so sometimes it can be, so L in this sense, for this, is the length of the wire itself. Okay, it's not this L. That's why in number one, when you calculate L, you put H, whatever this height was. So it's sometimes confusing because they will label this L, so you automatically think to plug in this L for here. But you remember that L is the length of the wire. L is just length, right? Not distance. I can easily change this to D, but that does not mean that this D over here is this one, for this case, where the wire is over here. It would be D plus W, right? So to make it a little easier, let's just change this to X. Right? Right now you have a distance of X. So your L is your length of the wire, which is here, H, times H, right? Okay? But remember what I said is the forces attract. Okay, if the force attracts, it moves in the negative direction, right? Because it's in the effects in the same. So your overall force will be towards the left. Because this way your system is set up, your positive x is to the right. So it'll be a negative, and your i's would be then I1, I2. I2. Okay? So just remember that this L does not always mean this, it means the length of the wire. Okay? It's not that, once you understand that, like, the concept sort of behind it, and understand the conceptuality, then it becomes fairly easy. Because then you can take any equation, you can just write down the equation, but then you'll know how to apply it. If you can have 1,000 equations, just like you have here, but if you don't know how to apply it, or what the variables exactly mean, then it's going to be a problem. It can be a little confusing. So if you want, you can like plug out your numbers or before you move on or whatever you're doing.
Can you go over number 5?
For the same one?
Yeah.
What's the magnitude of I3? Is this the 2 wire one? Okay. Chris, did you finish it? Yeah. Jason, can I erase this? Okay. So now you have 2 wires. Alright, and a rectangular loop. So this is current this way, let's call I1. We'll call this X, okay, not L, and this is 2X. 2X, and the current for this one okay, so, well, it says it's oriented in the positive Y direction, so I'm going to assume that the current also goes in this direction of an unknown current of I3. Okay, it's an unknown current. But we don't need to know the current, we just need to know which way the forces will act, right? And, oh wait, we wanted number 5, right? Oh, so we don't want, okay, I have to draw it out. And then, again, A, B, C, D. The current goes in the same direction. Okay. So what's the direction of I3 in the positive Y direction? And we know that because it says it's aligned in the positive Y direction, or positive Y axis, so we'll just assume, right? So now what's the magnitude of I3? Well, they tell you that the force, the net force on the loop is now 0, correct? Meaning that whatever repel force that was here, okay, and whatever attraction force was here, was now counteracted, okay, by some force, either repel or attraction between these two. Okay, and we know that because the current goes this way, and this current goes this way, that it was an attraction force, right? So that means that the repel force, whatever the difference is the force that we will use. That makes sense. So there was an repel force. Okay. There's a repel force here, right? Because they go in opposite directions. And there's an attraction force here because they go in the same direction. Okay, so when you have a repel, and you have an attraction. Over here, your currents will go in the same direction, so you'll have an attraction force. Let's do this. Okay, plus attraction. All right, that all equals to 0. Correct? You know these two, right?
Don't you also have a repel force between I3 and AC?
Oh yeah, you have that too. Oops. Okay. Yeah, these will repel. So you have a repel, an attraction, and you'll have a repel. Well, you'll have a stronger attraction because the distance is smaller. And here you have a stronger repel because the distance is smaller. I think the numbers might not work out like that because of the current, but intuitively, if you think about it, the distance is much smaller, right? So a attraction and a repel.
Okay, what's the green one?
Green one is this one, red one is this one.
Green.
Meaning
Oh, yeah,
between
yeah.
these wires. So this is this half between this wire, and this is for this wire. I just circled the first loop, but it applies to the whole loop. Okay. So ask you, what's the magnitude of the current? Okay. So you can use the equation, you can use this equation. So this equation is not like given, it's not stated, but walk through it. Okay. So you know that two forces have to balance out, right? So you have the force from current 1 and the force from current 3. So you can write out the equations for those. So we have I1 times, and then it's 2 something, whatever, over d distance, remember? And the force, it's mu over 2 pi d, where, or d, where d is whatever distance you have. So we'll just forget about all the constants, because it's just the lengths and all that stuff. We just have to worry about the distance, right? So it's 1 over L, right? Minus 1 over L plus W, which was the second wire. B and BC. Okay, that's for your first loop. This is the green stuff. Red stuff. This is the red one, right? Now for the green one, we'll have equals, because, equals, because it will cancel out. I3, whatever I3 is, okay, times the distances. So now you have twice the distance, right, because it's 2x. So it'd be 1 over 2L minus 1 over 2L plus W. Okay, and you see that's 2L plus W, because W will stay the same, but your L will be times 2. So it's not 2L plus W, because you don't have twice this W, right? It's just twice this L. Okay, so that's why over here, it's 2L plus W. Okay, now you can set this up and solve. Now you have all the knowns over here, right? You have all of the knowns. So you just need to find I3. You bring this over, and then you can solve for I3. Okay, so your final equation, I'm going to write it in blue, should come out as 2I1 times 2L plus W over L plus W. Right? You factor out the 2. That's what you think should come out as. So you can go through the algebra and put that. For me, I think it's just easier, like, don't even worry about the algebra. Just literally divide all of this, but find a number for this, find a number for that, and just divide. Don't even try to mess with the variables. Because if you mess with, like, it's such simple, like, numbers, right, it's just easier to find a number for all of this, find a number for all of this. And we don't even have to write it down. In your calculator, you can just do the first one divided by the second one and find it. So you don't have to worry about, rounding errors if you write down a number. You can just straight up divide.
Yeah, I think, yeah. Reduction is I think this is fine. Do you have the slides from the lecture?
I'm there on Blackboard.
I think he posts everything before exam. That's what he did last time. Like he posted all 8 to 15 before.
But
exam.
you have the
Let me check.
PowerPoints from last semester.
Classes?
For physics one.
Like, he, not last semester, like previous semester, like he posted PowerPoints from like,
Everything?
I only have up to capacitance.
Yeah, me too.
It
Yeah, I
doesn't.
haven't checked.
no, previous semesters.
Oh.
Yes, I have
The same thing?
Yeah.
It's not easy. Why is it thinking? Yeah.
When did next exam?
I'm just thinking, but there was 23.
29, okay.
Is that Monday?
Oh, that's, 29th is Wednesday, which makes sense. So the week, like 1 week after spring break.
From the lecture slides,
Mhm.
there are questions about port. Oh yeah, on the wire, I can't understand. What is, what's that?
Torque is our cross after, yeah. On wire 2, and the wire 1. Okay. Can I erase this? Yeah.
Yeah, I can.
We have a current coming out of the page, that's wire 1. This wire, current to the left, that's wire 2.
You. I can change your answer. Okay. So I thought this was ready on Instagram. No, it's not. When you were going over the grade, you I just this is what I control.
Okay, what I cannot create, I do understand.
I'm not 100% sure.
Yeah.
But I think I have an answer. So for this one, right, you want the, so the current is coming out of the page, so the forces will go like this, right? So under this circle. So it'll go like this, right? Right, and the force will be in this direction. Force will be in this direction, over here, and on this side, it will be down, right, which is what he wrote over there. So now, the torque is which way will the wire kind of want to rotate, right? That's what torque means. So, I believe that oh, okay. For this one, right? Now you have to remember this is also in 3D space, it's not just
Yeah.
2D, right? So if you like kind of sort of imagine 3D, it might make it a little bit easier. For this one, it's going to be hard to draw. I go like this. One second. That's wire 1 with the current coming out of the page. So like this. Okay. Wire 2 goes above it, perpendicular. Let's go like that. The wire current going to the left is wire 2. All right. So now if you look at it from this side, it's the exact same thing as we had last time, right? So this one, the current will go like this. The force, because the force will go like this, right? Will go up and over, right? Yeah, it's fairly 3D-ish. Force will go like that, right? And for this one, if you curl this way, at this point, the force will be going like that. Like this. If you curl to the left, the force will go like this. Right? It's going like that. I mean, sorry, the field.
They feel okay.
The field, not the field.
Yeah, that makes sense.
Right? When you do current, you put your current, you put your thumb in the direction of the current and curl your fingers in the direction of the field, like the B field, magnetic field, whatever it is. Right? So you see at this point, like if they ever touch, if the points ever touch, they're going to be going the same, like, it's hard to do with a 3D. It's like they're going to be going with the force here will be the field here will go like this, right? Will cross this like that, right? Just remember this is infinite, so it goes across. So it will cross like this, the wire.
Yeah.
It's kind of hard to draw. Just, okay, this red is the field from this wire, right? And it's infinite, so it goes across everything at every spot.
Mhm.
So eventually, it has to cross the field created by this one, right? Okay, and this one also creates a field at every spot.
Yeah.
Okay, so if we look at it back like this, when this crosses, when they cross, right, this will cross, the red one will cross like this. So the field will be like that. Okay? But then you have to remember the green one also has a field. So if you cross the green one, it will be going in the same direction, like this. If it goes, remember we said it goes around because this is the direction of the current. It will go like this. Right?
Yeah.
Is that like this? Okay. Okay. So at the point where they meet, it's going in the same direction, correct? Meaning the point, see it might be easier. Right there and right here. I think this is right. You can ask them in class tomorrow. I'm not sure exactly. You can ask them to go over it again, right? But I think so. You see, when the two fields meet, the arrows point in the same direction at that wire.
I thought the red one's going,
This way.
so
Yeah.
it's,
The red one's going this
yeah,
way,
so it's
and this one's going like this. Oh, wait,
one's going
This
this
way.
way, the other one's going
this way.
this way.
Yeah, they're going like this.
Mhm.
The red one's going this way. This one's going
Yeah,
this
that's
way,
wire too. Yeah.
right?
Mhm.
So the force this will produce is this way,
Yeah.
because it hits like this, right? And this, will, when it hits this field, will also be an up force. So because they're both pointing in the same direction, they're going to have a repel.
But they're going the same direction.
Well, you see the force like this,
Yeah, but one is going this way.
but it's going up, and this one's also going up, like this. I think so. I'm not 100% sure, but this is how I would think of it. You see, this one goes like this. Remember I told you to take the point and draw the tangent vector?
Yeah.
So, and let's just suppose the two fields will meet at some point. If you take the tangent vector of this, one like this, let's say you get something like this, right? Which makes sense. Like up. And at this, when they meet, it will be up.
Yeah.
So because they're both up,
up.
the fields will be up.
Torque.
The torque will be produced up. Because it's R cross F. If both fields, or both forces are being pointed up, then R is just distance. I think that's right. I'm not sure again,
Okay.
but that's the best explanation I could have. So I guess if the current was going in the opposite direction, meaning if this current was going down, right, and this current was going like this, then when they would meet, it would be zero because it cancels out. You see?
Oh, there's a one that torque is 0. Oh, yeah. No, there was torque.
I'm not 100% sure, but sorry.
What about the force?
The force.
In that case.
Well, the force would just act on a point, right? Like we did in the triangle problem, we just take a point at the origin and you find what's the force at that point from the different fields. So just say you take a point right here. You're going to take a point right here, and what's the force is acting by the two fields at that point? So, remember in the triangle problem we did like this? I said, what's the force of the origin? And I said, okay, this one, if it's coming out of the screen, it will be up, or something like that. Remember the three triangles? Something like this. So you just take a random point that you want to find the field at, the force, correct? And then draw your fields.
What about the net force on wire two?
The net force would be up.
You said it's 0.
Not sure. Yeah, sorry. I never did like weird problem like this. Did that help? She showed you.
Yeah. Oh. Wait, F is I cross B?
F is IL cross B.
Yeah. So what is that? Oh, I B. I B. Oh.
Where'd you get that?
Down.
Oh, okay. So net force is 0. Because it's symmetric. Yeah, okay, there's the answer. Like class or something? Oh, good luck.
Okay, I'll try to do. Oh, yeah. So when is torque 0 again?
When the fields will cancel out. Because it's R cross F, right? So the force, sorry, not the field, the forces. Because it's R cross F, and if F is 0, then it's just 0. So like she showed you, if this field is going this way, at this point, the field will be going this way, the tangent. At this point, it's coming back down, so the field will be tangent this way. And if you added it, now they cancel out.
Yeah.
Right. So then the net force would be 0.
What's it?
This right hand rule stuff it takes time to get used to it. R is the distance. Remember we did this in statics.
Yeah, no, but like direction of R.
The direction.
R has a direction.
R is just the distance. They're asking for a direction of R.
Direction of force.
Yeah, direction of force, not R. R is just a distance. I mean, you can convert it into a vector,
Yeah.
right? And then you can use A cross B equals AB sine theta. So R, F sine of the angle between them.
Yeah.
But most of the time it will just be 90. Especially when you're dealing with circles and like tangent circles. Every tangent at the circle will be 90 degrees, so the radius, right? That's the definition of like tangent. So that is just R times F.
I think statics is more straightforward than this.
It is. Statics was nicer, much nicer.